electric potential. Now we're looking at electric potential energy. So another way of defining electric potential is the amount of electrical potential energy per charge. Okay, I'll say that again. Another way of defining electric potential is the amount of electric potential energy for one charge. So the symbol, so this is electric potential, is the amount of potential energy, electric potential energy per charge. So the amount of potential energy, electric potential energy per charge an object would have, we'll make it clearer, at that point in the external magnetic field. So, the symbol then will be V. The equation, V equals electric potential energy over the charge, Q. And the units, since electric potential energy is energy, so those units are joules over charge in coulombs. Now, joules per coulomb has a name. Joules per coulomb is also called volts. So that is the unit we will use to represent the electric potential when we do the calculation. So because of its units, because the units are volts, electric potential is oftentimes called voltage because it's expressed in units of volts. Okay? Move this board over. All right. So because electric potential is dependent on distance, away from a charged object, we can also represent it as in terms of electric field of a given charge. Charged object, we can also represent it as electric field of a given charge. So we can say the voltage, or the change in volts, or the change in the electric potential, the difference from beginning to end, is equal to the electric field times the distance. So this represents, this is the difference in electric potential. Remember, that's the energy. The difference in electric potential, a charged object would have if it moved a distance d in an electric field E. So let's go back to gravitation. Just like I take this marker and I pick it up from here to here, I'm giving it potential energy. So this has potential energy here because it's not totally on the ground, and I'm giving it more potential energy. So there is a difference in potential energy. For gravitational potential energy, that difference in energy depends on the height that the marker is changing. Here, this difference in potential energy depends on the electric field and the distance you have moved it in that electric field. Okay? Now let's talk about electric potential difference or voltage difference. And then we'll practice. So when a charged object moves an electric field, we'll say when a charged object moves in an electric field, the electric potential energy of the object changes. Electric potential energy of the object changes. That means work is done. Work is done either on the charge or by the charge. So work, by definition, is a change in energy. In this case, a change in potential energy. So we can express work as the final potential energy 2 minus potential energy 1, or we can say work is equal to the change in potential energy. Taking this equation, so this is due to a charged object experiencing a change in electric potential. Remember, electric potential is dependent on where in the electric field the object is. And if you move it, you change its potential energy. Okay, so we can then say, we know that electric potential is equal to the change in potential energy over the charge Q. We already got that equation. I can substitute change in potential energy, I can substitute in work for that now. So this will look like this, work over charge. And if I just manipulate this equation, I will get work equals the charge times the potential, or times the voltage, or potential difference. Okay, so that's an equation that you will have at your disposal and you can use as well. And then we'll say the amount of electric potential energy a charged object Q would gain or lose if it were to be moved from V1 to V2. So this idea of potential difference or voltage difference will be huge in our next unit when we study electricity and circuits, okay? Because we're going to see what happens to voltage as charges move through circuits. All right, so once again, when a charged object moves in an electric field, the electric potential energy of the object changes. That means work is done either on the charge or by the charge, so we can express that work as the charge, the amount of charge in coulombs, times the difference in voltage or potential energy. Okay, so let's try these two equations really quick. I have two problems up here on the board we're going to do. So it'll help also to read through your notes one more time, because there's a lot of words that are similar here: electric, potential, electric field, electric force. So all these things sound the same, but they are not the same. So look through your notes a couple times and make sure you know the difference between these words. Okay, so this one says a positive 3.4 coulomb charged object gains 2.6 times 10 to the third joules as it moves through an electric field. Determine the electric potential difference. Is the charge going with the electric field or against the electric field? All right, so a couple things you need to identify here. This number, 2.6 times 10 to the third, is in joules. That should tell you that that is an energy measurement. Energy measurement. And this number is in coulombs, which should tell you that that's Q. All right, so we're going to use the equation voltage equals electric potential energy over Q, and simply plugging our numbers in, 2.6 times 10 to the third over 3.4 coulombs, and I get as my answer, you should pause and calculate, 764.7 volts. Okay. The second part of the question says, is the charge going with the electric field or against the electric field? So remember that the electric field is field lines that go from positive to negative. So if this is your electric field here, and in this case you have a positive charge in that electric field, that positive charge is going to repel the positive end of the electric field and will attract the negative end of the electric field. So that positive charge will also move in this direction. So the positive charge will move with the electric field. The second problem, how much energy would an electron gain if it is moved through a potential difference of 23,000 volts? So potential difference is V, right? That's why the units are in volts. And one number that you need to know that is not given to you here is that of the electron. The electron has a charge of 1.6 times 10 to the negative 19th coulombs. Okay, so this is, again, the same equation. V equals potential energy. Oh, no, sorry. Wrong. Let me see. How much energy would an electron gain? Yeah, that's right. So V equals PE, potential energy, over Q. And in this case, I have the V, 23,000, equals, the potential energy is what I'm looking for, and my charge is 1.6 times 10 to the negative 19th coulombs. Okay? So just cross multiply here, pause the video, get an answer, and then check back to see if you did the right math. And you should get 3.68 times 10 to the negative 15 joules. Okay? All right, again, go back through and make sure you read your notes and understand, and then follow the rest of the instructions on haiku for today.